When we left off yesterday, we were talking about order of operations and talking about operations with whole numbers. And one of the small concepts that had big consequences for us, I should say, was that idea of place value. And we talked about those place values starting from the decimal and working our way back to the left as being the ones, tens, hundreds, and then the 1,000s, 10,000s, 100,000s, and so on. So anyway, we talked about those place values, but there's something more to it. After we mentioned place values, we talked about exponents and powers. If we look at this really closely, 10, of course, could be thought of as 10 to the power of 1. 100 is 10 squared, or 10 to the power of 2. 10 to the power of 3 would be 1,000. 10 to the power of 4 would be 10,000. 10 to the power of 5 would be 100,000. The 1 is what we define to be 10 to the power of 0. In fact, anything to the power of 0 is defined to be 1. Why is that? Well, because in math we have a tendency that if there's something that doesn't make sense, we look for a pattern and we define the answer to be whatever fits that pattern. Now, the rest of these all make sense. 10 to the power of 1 is just 1 10. 10 to the power of 2, it's 2 tens multiplied together. 10 to the third is 3 tens multiplied together. But 10 to the 0 doesn't make sense. How can you have 0 tens multiplied together? You really can't. But we define it based on our patterns. 10 to the third was 1,000, 1,000. 10 to the second power was 100. 10 to the first power is 10. And we look at this to establish the pattern that when this power goes down by 1, our result over here is divided by 10. So if we were to keep going, 10 to the power of 0, well, if we divide by 10 again, 10 divided by 10 is 1. It has to be 1. When we talk about decimals, we'll keep going with this, and we'll actually define negative powers of 10. The point being is these place values are all powers of 10. Our number system is what we call a decimal number system. Deci is the abbreviation or the metric prefix for 10. So it's often called also a base 10 numbering system. Now, if you were to get into computer science, we would talk about other base numbering systems. Binary is a base 2 number system. It goes just all zeros and ones. Or hexadecimals, base 16. Now, we're not going to talk about other number bases, but we are going to talk about a number system that does have a different base. A lot of us look at something like this. And think that that is totally different than the whole numbers that we talked about yesterday. But it isn't. If you recall, 300 and just the number 372, this was 300s plus 7 tens plus 2 ones. We could have shortened that up and said this is 3 times 10 to the power of 2, because hundreds are 10 to the 2, plus 7 times 10 to the 1 is the tens place, plus 2 times the 10 to the 0 for the ones place. This here is our expanded form of that number, 372. Well, with algebraic numbers, we always write the number in expanded form. This here, 3x squared plus 7x plus 2, is just the expanded form of a number. In algebraic numbers, we have to write the place values in there all the time. This is the x to the 0, or the 1's digit. This is the x's digit. This is the x squared digit here. Now they look very different because we've got variables in it, and most of us lock up a little bit when we see the variables. But it still behaves exactly the same way as this 372. That's why in the last class I wrote out 372 in this expanded form, 300, 7 tens, and 2 ones, because in that form it behaves exactly the same way that this does. We talked yesterday about adding and subtracting and multiplying and dividing numbers and the rules that go along with it. We saw that 5x could be added to 3x because they have the same name, x. So 5 plus 3 is 8, and we keep the same name of x. We also saw that 4x and 7y could not be added together because they have different names, x and y. Those are different place values. It doesn't always stay quite that simple. It can be a little more complex. For example, this one, 5x squared plus 2x, we cannot combine those. In fact, those are actually just a single number with two separate digits. You look at those and think, well, they're both x. Why can't we combine them? They have the same name. But they don't. This is x squared, and this is just x. Think about it. That'd be like taking 500 and the 20 and adding the 5 to the 2. We can't do that because they're in different place values. Same thing here. This is x squared, and that's just x. They're in different place values. We have to leave that as 5x squared and 2x. Just like this, when we combine them, would still be 500s and 2 tens to make 520. The biggest difference between our whole numbers that we talked about yesterday and these algebraic numbers is the fact that an algebraic number is always written out in expanded form because the place values can be anything. They're not always ones, tens, hundreds, thousands. They could be ones and x's and x squareds, or they could be ones, y's, b's, and c's, or whatever. And also, like I showed you yesterday, they don't always get written in order. We could have 7x plus 3y plus 9x squared as an algebraic number. Now, just like with the whole numbers, we talked a little bit yesterday about putting them in descending order. In other words, the larger place values go first. The thousands come before the hundreds, which comes before the tens. The bigger place value goes first. Normally, we would write this with the 9x squared at the beginning because it's the larger place value. Now, the 7x and the 3y don't really have an order to go into. So if I give you some random digits like 8x plus 4y plus 3x plus 9y, just because the x and the y are not the same names does not mean we can't simplify this a little bit. We can still combine the things that do have the same name. We have the 8x and we have the 3x, which are going to combine to make 11x. Good. We have 4y and 9y, which will combine to make 13y. Now, we look at that, we got 11x, we have 13y. We need something to connect them in here. Well, is this 13y positive or negative? It's positive, right? So it's going to be a plus there. When we're looking at numbers, especially algebraic numbers, the symbol in front of each digit is also a positive and negative. It's not only addition or subtraction, it's also positive or negative. This is plus 4y because that's a positive 4y. Plus 3x because that's a positive 3x. This was a positive 13y, so that was plus 13y. That brings us to the second big difference between algebraic numbers and whole numbers. Not only do we have to write out the place values, but in algebraic numbers, each digit can be positive or negative on its own. When we're dealing with integers, if I have a negative 239, that means that is a negative 200s and a negative 310s and a negative 9 1s. Every digit of that number is negative. In an algebraic number, however, we can have a positive 2x squared, a negative 7x, and a positive 8. Each digit of that algebraic number can be positive or negative on its own. The operations with these numbers then from here are exactly the same. To work with them, we need to understand a little bit about working with integers, in other words, negative numbers. So the next thing I want to do is take a little side journey into integers and look at how do we operate with numbers when they're not all positive. One of the tools that I like to come back to whenever possible, because it really is the basis of a lot of our number system, is the number line. We're going to go both directions here from 0 because we are going to deal with negative numbers. Now, we've all used number lines at some point in the past. We might represent the number 6 with a dot here at positive 6. But in real number theory, there's a little bit more to a 6 than just that dot on the number line. A 6 can be represented by something called a vector. Now, you don't need to know that term, but what it looks like is important. It's really a fancy term for a pretty simple concept. To represent 6 on a number line, we take a vector that starts at 0 and goes to 6. So all it really is an arrow that starts at 0 and goes to the number that we're specifying. Now that vector doesn't have to stay there. It can get moved around this number line wherever we want it to. It can move left, right, wherever we want it to go. So if we have the problem 6 plus 2, we've already got the 6 on there. 2 would look like this. The mathematical operation of addition is telling us to take the two vectors and combine them together. So we take the 6, we put the 2 on the end of it, and the result is a vector that is now 8 units long. So that's why, I mean, most of us, we've been adding and subtracting for so long, we don't even think of why 6 plus 2 is 8. But that's why, is because we're taking those lengths, those little vectors on the number line, and we're combining them together to get a total length. You could almost think of it as taking pieces of string and gluing the ends together to get a longer string. It's kind of
integers, and then you start scaring me because isn't a positive 2 supposed to be taken off there? I start getting confused right in there.
No, addition, of course, we're just adding the links together. But what if? Here is the big difference. The next step is 6 plus a negative 2. So now the 2 isn't pointing in the positive direction. So we get rid of that one. That's not what we're using anymore. A negative 2 goes this way. But now when we go to combine those vectors, we move the negative 2 with the 6. And since it points in the opposite direction, they work against each other. And we end up at 4, positive 4. We're still on the positive side of the number line, is here's 0, right here. We've gone to the positive 6, and then we go back 2, leaves us at 4.
I thought that was the negative side of the 0.
Nope, the negative side's over here. This is the positive side. The negative 2 started here going to the negative side, but remember, we move it around on the number line. And when we moved it over here to combine with the, oops, gotta be careful there. When we moved that negative 2 over here to combine with the 6, it's starting at 6 now and going back 2.
So basically a positive plus a negative is you're always going to...
Not always. Well, it does turn into subtraction.
But then whatever the bigger number is whether it's going to be a positive.
Whatever the longer vector is determines whether it's going to be positive or negative. Exactly. Now, I don't expect that you're going to draw out number lines when you do addition and subtraction with negative numbers. But I do keep these images in my head because it does help me figure it out. This one had to be a positive 4 because the positive vector was longer, which means everything stays on the positive side. Even though this 2 goes in the negative direction, it's not long enough to get us back past 0. Does that make sense? Yeah. Okay.
I've never quite seen it that way before, so it's a total new concept.
Sure. Well, and that's, most of the time you're sitting there thinking with rules of, okay, which one's bigger, so that's where it's got to be. The rules are nice, but there's a place the rules came from. And to me, it's easier to know where the rules came from than it is to just memorize the rules.
But yeah, I always been taught that, here's 0, and positives on this side and negatives on this side. So if you...
Okay.
Yeah.
Something got backwards then. If you're looking at place values, all the positive place values are on that side. But for the number line, for graphing and number lines, going to the right has always been our positive direction. Okay. So like I said, when we're adding and subtracting, I don't expect you to always draw out these number lines, but keeping those vectors in the back of your mind is very useful. If I have something like 5 plus a negative 7, what I'm thinking of here is, okay, there's positive 5. Negative 7 goes the opposite direction. Is it longer or shorter than the 5? It's longer, so it's going to take me past 0 into the negative side of things. So I know the result of that is going to be negative. And how far does it go past 0? 2. Because the 7 is 2 units longer than the 5, it goes back into the negatives 2 units. Or if I have negative 4 plus 7. Again, I'm thinking of my vectors. I have a negative 4 to start with. So I'm starting out in the negative direction. Well, positive 7 takes us in the other direction. And it's longer, so it takes us past 0 back to the positive side of things. So that's going to be a positive 3. The 7 takes us past 0 by 3 units. Or we could have negative 8 plus 2. Again, negative 8 goes to the negative side of things. Positive 2 goes the other direction, but it is not long enough to get us back to 0. So our answer here stays negative 6. You can see here, even though the operation we are doing is addition on all of these, sometimes we're really subtracting. Because here, even though it was negative 8 plus 2, we did 8 minus 2 to get the 6. This little picture told us that the sign had to be negative because we stayed on the negative side. Same here. Our little picture of our vectors told us that does come out to be positive, but the result of 3 came from 7 minus 4, the difference in their lengths. This one, of course, 6 plus 2, we had to add to get 8. And there are other cases where we add, where we might not realize it. Negative 3 plus a negative 5, if we look at that picture, here's negative 3. Well, negative 5 goes in the same direction. There we go. Our answer is negative, and we're combining the two links to make 8. So that's what this picture tells me. I don't have to draw out the number lines and do everything to scale. But thinking of the vectors tells me, first of all, whether my answer will be positive or negative. And second, whether I'm really adding the numbers together or subtracting the numbers from each other. So that's addition. And of course, that works with larger numbers too. I might have 239 plus a negative 114. My picture would be 239. Negative 114 goes the opposite direction, but it's shorter. So I know my answer is positive, and it's the difference between those two numbers. So I'm actually subtracting a 114. Get 125. When we actually do subtraction, though, let's look at 6 minus 2. If we think about what that would look like on our number line, it actually makes sense. We'd go to 6 here, and then we go back 2 to get to what we know the answer is 4. But if we look at that picture, it looks an awful lot like something we did before up top here. It looks exactly like the picture we did for 6 plus a negative 2. In fact, it is the picture for 6 plus negative 2. The reason is the operation of subtraction is really not its own operation. We hinted at this yesterday, that addition and subtraction were the same thing, and they are. Subtraction is a shortcut. This symbol right here that we all know as the subtraction symbol means add the opposite. Now, we're also used to seeing subtraction that we look at this 6 minus 2 and we instantly know it is 4. But what it is really telling us to do is take 6, and subtracting 2 means we are adding the opposite of 2. In other words, plus a negative 2. Now, for the most part, it's easier for us to just do 6 minus 2 because we're used to doing it. But when we start throwing in the negative numbers, for example, if I had negative 5 minus 7, here it might be easier for us to think of this as negative 5 plus, what's the opposite of 7? Negative 7. Negative 5 plus negative 7 makes more sense to me than negative 5 minus 7. We know this is going to be what? Negative 5, negative 7 makes negative 12. Good. This is a little bit cloudy to me. It's not as obvious. So when we're dealing with, when we have negative numbers, if we have integers involved, it's almost always beneficial to change subtraction into adding the opposite, plus the opposite. Okay. So if I have 4 plus a negative 9, or sorry, 4 plus 9. I meant to say 4 minus 9. It's easier for us to think of that as 4 plus a negative 9. So now this is positive 4. Negative 9 goes the other direction, and it makes it past 0. So the result is negative 5. And here's the one that always seems to be the showstopper. 7 minus a negative 4. Now, a lot of times your book will write this like this with parentheses around it, just so you know the negative goes with the 4 and stuff. Don't be confused by the parentheses. They don't. All they're doing is separating the negative from whatever the operation is. But 7 minus a negative 4 could then be thought of as 7 plus, well, what's the opposite of negative 4? Positive 4. 7 minus negative 4 is just 7 plus 4, which is 11. When we subtract a negative, it becomes plus a positive. It's one of those rules you were probably told, but the reason why is right here. So if we have negative 6 minus negative 3, that is going to become negative 6 plus positive 3. Good. So now we have the negative 6, we have positive 3. The answer is, careful, go back 6 and then forward 3, it's a negative 3. Yep. That's going to take a while to get used to. Try not to get frustrated. It's something that we're going to have to go over and over and over the next several weeks. On a larger scale, we could end up with 38. Let's go negative 38 minus 17. That can be thought of as negative 38 plus a negative 17. And the picture would look like this. Negative 38, negative 17 goes the same direction. So the answer is a negative, because they're on the negative side of 0. And since they go the same direction, we're adding the 38 and the 17 to get 55. So negative 55 would be that result. Multiplication and division with our negatives is much simpler. Let's go back to our definition of multiplication that we talked about yesterday. 5 times 3, remember we said that really meant repeated addition. 5 plus 5 plus 5, which makes 15. So it's not much of a stretch to do negative 5 times 3, because that's just negative 5 plus negative 5 plus negative 5, otherwise known as negative 15. Now 5 times a negative 3 is a little trickier. Again, your textbook will probably put that negative 3 in parentheses like that. I can't take 5 and multiply it by itself, or add it to itself negative 3 times, can I? But I can take negative 3 and add it to itself 5 times. And the result will be, again, negative 15. We've all been taught those rules of when you multiply a positive times a negative or a negative times a positive, the result will be negative. This next one, negative 5 times negative 3. Again, your book would probably put parentheses around it like that, maybe even like that. We all know what the answer is because we've been taught that a negative times a negative has to be positive, right? Negative 5 times negative 3 would be positive 15. But most of us have never been shown why. Mainly because when we look at that, it really doesn't make sense. How can I add negative 5 to itself negative 3 times? I can't. And I can't switch them around either. I can't take negative 3 and add it to itself negative 5 times. That doesn't work either. Well, like we talked about with the powers of 10, where we said 10 to the power of 0 has to be 1, the same thing applies to integers. This doesn't make sense. Multiplying two negatives doesn't make sense. So we look for a pattern, just like we did with the 10 to the power of 0. And we define the result to be whatever makes the pattern continue. So let's start out with that negative 5 times a positive 3. That is a negative 15. If we do negative 5 times 2, that's going to be negative 10. Negative 5 times 1 is going to be negative 5. Good. Now we look for the pattern. Here is if we were starting with negative 5 every time, when we decreased what we multiplied by 1. In other words, when we went from 3 down to 2, our answer became larger by 5. It went from negative 15 up to a negative 10. If we went from 2 down to 1, our answer got larger by 5 again, from negative 10 up to negative 5. Well, let's see if that pattern continues. If we did negative 5 times 0, we get 0. Anything times 0 is 0. Well, did the pattern continue? Well, we went down by 1 here, and we went up by 5 for our answer. So yes, the pattern did continue. So if we keep going, negative 5 times negative 1 times negative 1 has to be a positive 5. The only reason is because it's what keeps this pattern going. So negative 5 times negative 2 has to be a positive 10. Negative 5 times negative 3 has to be a positive 15. So when we multiply two negatives, the answer is a positive, but the only reason is because it makes our pattern fit. So the short story, the shortcut is, if I have a positive times a positive, of course, the answer has to be positive. 7 times 3 will be 21. If I have a negative times a positive, the answer will be negative. Negative 2 times 8 will be negative 16. Good. If I have a positive times a negative, the answer will be negative. 5 times negative 6 will be negative 30. So you can see I'm just multiplying the numbers. 2 times 8 is 16, and then figuring out whether it has to be positive or negative. 5 times 6 is 30. It has to be negative because it's a positive times negative. When we multiply two negatives, we have to have a positive. Negative 4 times negative 6 will be a positive 24. Perfect. Division, we said, follows the exact same rules as multiplication. And it does. If I have a negative divided by a positive, the answer will be negative. Negative 18 divided by 3 will be negative 6. A positive divided by a negative will be negative. 24 divided by negative 6 will be negative 4. And a negative divided by another negative will be positive. Negative 36 divided by negative 4 will be a positive 9. Good. Any questions? Okay. Well, let's take this back now to our algebraic numbers. What if not everything is positive? What if we have 8x plus 3y minus 5x minus 7y? We can combine the things that have the same name. 8x, and this isn't 5x here, this is negative 5x. 8 and negative 5 make,
Negative 3.
careful, positive 3, right? Positive 8 negative 5. Stays on the positive side. Because the positive vector is larger, so it stays on the positive side. So that'll be a positive 3x. Here for the y's, we have 3y and negative 7y. Well, we start at 0, we have a positive 3, but the negative 7 is bigger, so this one will be negative 4y. Good. And it's negative, so the negative sign is what connects the two together, so it's 3x minus 4y. So this here solution that we just came up with can be read in one of two ways. The way I just said it, 3x minus 4y, or it can be read as 3x and negative 4y. They mean the same thing. So here, tell me what to do.
Combine the A's.
Okay, so we got 5a and
A negative 7.
negative 7a, which makes
-2.
perfect. Positive 5, negative 7 does make negative 2a. Then we have to combine the b's, 9b and negative 2. So 9 and negative 2 make positive 7b. And since that's positive, we'll put a plus in front of it. So we have negative 2a and plus 7b. We can work with numbers bigger than just single digits like this. We can work with this. Now, when we look at this, the first thing we see are parentheses, which every time we see them, it should scream at us, do something here first. But in this case, there's nothing to do. Just like when we were doing our negatives up here, the parentheses just separated that number from the other one. Same thing is going on here. This 3x plus 2 is really a single number. It's a two-digit algebraic number. It's, instead of being 3 10s and 2 1s, it's 3 x's and 2 1s. Plus 5 x's and 4 1s. Now, we've all been taught different methods for combining those, but really we can use the same rules we've used for whole numbers to combine these algebraic numbers here. We can set them up, 3x plus 2, 5x plus 4. Just like with the whole numbers where we were careful to line up the columns with the same place values, here we line up the 1s and we line up the x's. And we're just going to add straight down those columns. 2 plus 4 is 6. Now it is a positive 6, so we put plus 6. 3x plus 5x is 8x. So 3x plus 2 plus 5x plus 4 is 8x plus 6. We can add a digit there. Like this. But again, it's still the same way. We're going to line up our columns. So we're putting the 4x squared under the 2x squared, the 9x under the 5x, and the 5 1s under the 3 1s, and we're going to add down the columns. 3 plus 5 is 8, so that's a positive 8. Put a plus in front of it. 5x plus 9x is 14x. Positive again, so we put a plus in front of it. 2x squared plus 4x squared is 6x squared. Good. So that is the solution to this. Where it gets a little trickier is, remember, each digit can be positive or negative in an algebraic number. So we can run into this. One thing I should point out, by the way, is notice in algebraic numbers we don't have to carry. It's okay to have 14 here. We don't carry a 1 or anything like that. So it's actually a little bit simpler even than whole numbers in that sense.
Can I ask a question now?
Sure.
What would happen if you had a 2x squared and maybe a 5x squared and a 5x to the power of 3?
I'll get to that in a minute.
Okay.
Good question. So here for this one, we're going to line them up again. But now we have some negative digits in here. 4 plus a negative 11. Let's draw the picture. We've got 4, negative 11. That should give us a negative, close, 7. There we go. Negative 7x plus 9. Well, negative 7 plus positive 9, positive 2x. And 5x squared plus 2x squared is 7x squared. What if we have something like this? Does anybody see the potential issue here?
4x squared and 2x.
Perfect. This is x squared, and this is x to the third. They're not the same place value. I can't combine those. This is just like if I had 4 hundreds plus 3 tens plus 9 ones. Now I realize that's a negative, but I have to keep positive in my whole numbers. And 2 thousands plus 6 tens plus 2 ones. When I write this number here out without the expanded form, without the place values, what do I have to do? Well, it's 2,000, 0 hundreds, 6 tens, and 2 ones. It gets written like that. But in the expanded form, I don't put the 0 hundreds in here because I don't need it. But when I shorten it up, I have to put that 0 in there as a placeholder to fill up that hundreds place. The same thing is going to happen over here. This still gets written as 4x squared plus 3x and a negative 9. This, however, is 2x to the third. We put a 0 in the x squared place. And this is not positive, this is negative 6x plus 2. We're still adding here, so we're going to add down the columns. Negative 9 plus 2 is negative 7, good. 3x plus negative 6x, negative 3x. 4x squared plus 0x squared, 4x squared, and that's positive, of course, and the 2x to the third that we don't have anything to combine with. So you can see it's really pretty much just like working with whole numbers. What about subtraction? What if we had 5x squared plus 6x plus 9, and we have to subtract 3x squared plus 8x plus 2. Well, really nothing changes. We line up our columns just like we did with our whole numbers. only this time we are subtracting down each column. What is 9 minus 2? Positive 7. 6x minus 8x. Negative 2. 6 minus 8. 6 minus 8 is negative 2. 5x squared minus 3x squared. Positive 2x squared. So there it is. Now, of course, it can get trickier because we can throw some negative digits in there. We could have 3x squared minus 9x plus 7 minus 2x squared plus 5x minus 4. So again, we write this out, lining up our columns. And we are subtracting down the columns. So this is 7 minus a negative 4. Now, when we look at that, what do we change that to? Yeah, 7 plus a positive 4. So that becomes a positive 11. Here we have negative 9x minus 5x. So I'm just going to look at the numbers. Negative 9 minus 5, we change that to negative 9 plus a negative 5, which is negative 14x. Negative 9 plus negative 5 is negative 14.
You know, that screws me up because I always used to learn, I guess, you know, with that negative and a positive equals a negative, and that 7 minus 4.
Negative and a negative or minus a negative is adding a positive. But here, a negative minus a positive still ends up negative because both of them are going in the negative direction here. And that's the key, is change it to addition and then look at the vectors and see which direction they go. Here, this one's a little simpler. 3x squared minus 2x squared is 1x squared. Now, we don't have to necessarily write the 1. We can just write x squared. Whenever you see something like that, x, y, or whatever, it implies that there's a 1 there, but we don't necessarily have to write it. Well, with that, it looks like a good place to take our first break, so we will end this part of the lecture here.